Okay, so the third problem that deals with buffers and titrations and whatnot is the following. Calculate the pH of a solution formed by addition of 26 milliliters of 0.4 molar potassium hydroxide solution to blah, blah, blah. So we are starting with a weak acid, and we are partially neutralizing it by adding strong base. What's a good place to start?
Write the equation.
Sure. HA plus OH minus reacts to form water plus A minus. So it's the same equation as in a titration, but you can tell simply by glancing at the quantities that it's not going to be a complete neutralization. You're not going to go all the way to the end point. So what do we want to do? Teo.
Well, we know we're going to be creating a buffer.
Correct.
So we want to do the stoichiometry, then use the resulting concentrations to figure out the pH of said buffer.
Excellent. A problem like this is a two-step process. The first step is just stoichiometry to figure out what your concentrations of weak acid and conjugate base will be after the partial neutralization. The second part is equilibrium, where you take those concentrations and use them to calculate the pH, either by plugging into the rearranged Ka expression or into our friend the Henderson-Hausbach equation. So where shall I start?
Well, why don't we just figure out the moles of hydroxide and moles of folic acid.
So our initial moles of hydroxide, simply molarity times volume, 0.400 molar times 0.0260 liters equals, and our initial moles of HA is 0.625 molar times 0.0370 liters. And by the way, I'll indicate that these are our initial moles.
And we're going to get 0.0104 molar and 0.023125 molar.
2,
15.
Okay. Since we are going to be doing subtractions with these quantities, I'm going to round to the correct number sig figs, which is 3 here. So there's my initial moles of HA. Okay. To aid you in the stoichiometry, remember we had a device that we called it not an ice table but an earth table, which basically lets you calculate how many moles remain. If that confuses you, you don't have to do it by any means, but I'll do it here. So HA, OH minus, A minus. I is the initial number of moles, which is 0.0232 and 0.0104. R is the moles that react. And pretty obviously, hydroxide here is the limiting reactant. So minus 0.0104, minus 0.0104. The moles of conjugate base formate ion that are formed are equal to the moles of hydroxide added by stoichiometry, so that's plus 0.0104. And F is the final number of moles of each substance present after the neutralization. So this is 0.01, so sorry, this is 0, approximately 0. This is 0.0104, and 0.0232 minus 0.0104 is 0.0128.
Yeah.
Is that correct?
It's, when you don't do the rounding immediately, it comes out to 0.0127, but what the hell.
Well, you should round. All right, those are moles of weak acid and conjugate base remaining, but we want molarities, so what do we want to divide those by?
Total
Volumes.
But the total volume of the two solutions combined, 26 and 37, is 63.
Wait, if we're plugging them into Henderson-Hausbach, do we actually...
Technically not, but I like to anyway. I don't know. Call me OCD, but I like it. Yep. Point. Oh.
It's John.
Hi, Jahan. How are you?
Good, how are you?
Fine, thanks. All right, so we will divide by 0.0630 liters to give us.
Oh, how we're going to do it. Okay, hold on. 0.0104 divided by 0.063. 0.165.
Yes. So 0.165 molar is our concentration of conjugate base produced. And
No, that should be the concentration of...
I thought you said 0.0104.
Yes,
Yeah.
yes, you're right.
We're doing the last problem.
On the pH.
Yeah. And what do you get further?
0.023 molar. 0.203 molar, sorry.
0.203 molar HA. So looking at these concentrations, 0.203 molar weak acid remaining, 0.165 molar conjugate base formed, would you consider those to be comparable in magnitude?
Mhm.
So would you consider this to be a buffer solution?
Yes.
It is. Okay, so now, so that's the stoichiometry part. For the equilibrium part, then you can either use the rearranged Ka expression, or if you prefer, you can use the Henderson-Hausbach equation. Anybody got a preference?
Henderson-Hausbach.
All right. So the HH equation is pH equals pKa plus the logarithm of the ratio of the conjugate base to the acid. I gave you the pKa. It's 3.75 plus the logarithm of 0.165 molar over 0.203 molar equals 3.75 plus. I kind of like to calculate the intermediate quantities.
0.0902. Well, negative 0.0902.
902, which is equal to
3.66. roughly.
3.66. Excellent. Okay. I hope there's a bumper problem on the exam, because you all knock it out of the ballpark.
Wonderful.
Yeah.
Say bye-bye.
Bye-bye, Jared. Oh, it was addressed to Jared. Oh, not this again.